Are the quizzes beginning next week? And also, are they're just going to be pulled from any of those?
Any of those problems, yeah. Yeah.
Okay.
That are asterisks.
Yeah, the ones that have the star by them, yeah. Yeah. And I'm just going to kind of keep updating that pile of stuff. I think it's just like stuff that's like fair game. You know, I mean, they're good, like qual fair game questions, you know, and so I'm just going to pull from that. All right.
Okay. But there's not going to be like a sense of like this week, this subset of those problems are
well, I'm going to try and go in order, you know,
okay.
And I've kind of broken, if you can see that, like there's like a little spiel before some of them, right? And I've kind of broken them up by topic, but I'm not going to say exactly, you know, I'm going to reserve the right to give you problems from older things if I want to, you know, keep you on your toes. Okay. So problem 3, you ask, what does this mean? Okay, so yeah, so AM is Atia McDonald. So, and then DF is Dummett and Foote. And so I don't have my copy of Atia McDonald here, but there's it turns out that I think only in the first chapter of Atia McDonald there's actually problems written in prose. So yeah. So those two problems. The first problem is about radicals, the definition of a radical of an ideal. And the other one's about I think saturation. Or no, it's not about saturation. It's another one of these things where you have to do. It's just like checking properties of something, but it's a good sort of exercise to get your hands dirty with like dealing with this is an element of this. This is raised to a power, so that you check, you know, that it's in the ring. It's just kind of like yeah. We can talk more about that afterwards. Okay, so we're going here. We got the app open. So this is again in the chat. All right, and I'm just going to continue with where we were. So, and I think I didn't do the existence of maximal ideals, right? So, and you guys can you guys see this? Oh, yeah, I see. But can you guys see this on Teams or no?
No, because you have not shared yet.
I thought I had shared. It says start. Okay.
The old app link.
Oh, it does the photos. Okay, to Microsoft Teams. There we go. There we go. Okay. So what were you saying about the old app?
I don't see the link anymore in Teams. Maybe I need to click on something. I had a.
Let me just copy this.
I think it's hidden under like a reply, Rick.
Okay.
Yep. Yeah.
One of the first.
Is there a way to pin these?
I
like
found
in Discord. You guys know?
Ooh, that's a good question. Can you pin?
I'll ask. We'll try and figure out if we can pin it later.
Yeah.
All right. Okay. So I mean, feel free to put that in other places in the chat too. So like, you know, if you want to repost it. Oh, I also made a wiki, right? So if you guys want to organize information on a wiki, right? You guys can do that. So there's a wiki in Teams that all of you can edit. All right. So existence of maximal ideals. Yeah, was there another question?
You can pin, by the way. There's like a button. If you click the 3 dots next to a message, you can just click pin.
Okay. Can you pin?
Yes, I'm currently pinning all the.
Yeah, Colin just pinned all of the
important stuff.
Okay, great. Thank you very much. All right. So let's do existence of maximal ideals. This is not too big. Let's do. Let's see. Kind of nice. Okay. I can't get rid of those dots. Whatever. Okay, so let me remind you what the definition of a partially ordered set is, because we're going to have to do. Okay, so let's do. So this is the kind of one of the topics, and then within this we need to talk about Zorn's lemma. So Zorn's lemma is a thing that's equivalent to the axiom of choice, and it's super useful. So okay, so let me give you a definition. Okay, so let's recall that a partially ordered set, or a poset, So this is a partially ordered set. Is a pair consisting of a set and a relation. So so a set and a relation where S is a set and this thing here is a relation on S, which is reflexive and transitive. Maybe you've become neurotic. We won't need this, but about like, so this is a category. Objects here are partially ordered sets or posets. Morphisms are ones that respect the inclusion, okay, if you care. But we don't really need the morphisms. Okay, so the best example here, is, so take, so let X be a set. Then the power set of X. And there's notations for the 2 to the X, so this is the same thing as P of X. This S, right? With inclusion of subsets is a poset. Okay. All right. So there's not, so like things don't have to be comparable. Okay. The lattice of subgroups is a poset. Every lattice, a lattice in terms of sets with inclusions are posets, right? Or not sets with inclusions, but you know, a set with an ordering operation. Okay. Okay. So let me give you a definition. So so let S, this thing, be a partially ordered set. So I don't know why I'm writing it in all caps, but okay. But a subset T of S is called a chain if for all X, Y, and T we have X less than or equal to Y or Y less than or equal to X. So it's just essentially like, it's what you'd think, you know, it's like a line of things. Okay. All right. And so now I'm just going to state Zorn's lemma because we're going to use it now. So Zorn's lemma says the following. So it says that if every chain has a bound so if every chain has a bound in S, not necessarily in the chain, right? Then there's at least one maximal element in the set S. Okay, so it says let S, this thing, be a poset. Okay, so if every chain T has an upper bound in S. So this is important that it's in S, not necessarily in T. Then S has at least one maximal element. Okay, so maximal elements may not be unique, but this is just saying that they exist. Okay, and so let me just remind you what I mean by a maximal element. Okay, so an element, so you have to give some definition of what maximal means, right? So an element M in S is maximal if whenever you have some other thing that is bigger than it, it must be it. Oh, M Okay. So that's what it means for something to be maximal, right? So if you have something that's bigger, then it's got to be equal to it. All right. Okay, so let's prove a theorem. All right, so is that clear? What Zorn's lemma says? So it doesn't necessarily need to be a countable chain, right? So it could be, you just have to have them in a line. Okay. So let's now do the existence of maximal ideals. Okay, so here's a theorem. All right. So 1, all rings have maximal ideals. Okay. 2, so for every ideal that's not the whole ring, so R here is a ring, right? Where I is not equal to R, there exists some maximal ideal M in R with I contained in M. Okay, so this is the theorem. So in particular, every non-unit element is contained in some maximal ideal. That's useful. Okay. So it's kind of like a silly thing, right? So this is what, like I was saying before, that the silly things are sometimes the harder things to prove, and this one turns out that you need the axiom of choice. So if you were to try and do it without the axiom of choice, you'd be in trouble. That's kind of like one of the things about these proofs with axioms of choice is like, you have to apply it, right? You don't know, you have to apply it in order to get the things done. So if you sit around trying to do it without this, you're not gonna have a good time. Okay. So, but I mean, I'm not saying that as a rigorous statement. I don't know whether or not this is, independent of ZF or something like that. So anyway, but set theorists know the answer to that question. So if you're going to ask Dan Hathaway, he would know. Okay, so in the notation as above, okay, so what we're going to do, we're going to prove that all rings have maximal ideals. So in the notation of the previous section, right? So we need to make a partially ordered set, and we need to of the previous section. So we're going to pick a partially ordered set, and then we're going to show chains have bounds, right? So S is going to be the set of the collection of ideals. So S is going to be the set of I in R, where I is not equal to R. Right? Okay. So these are proper ideals, right? Okay. So we will show that every chain has an upper bound. So we need to show that every chain in S has an upper bound.
Do we know that set isn't empty?
The zero ideal? Yeah. So the zero ideal, I think that's if you have so principal ideals, yeah, is another one. So all principal ideals give you ideals, but I guess you don't know that the zero ideal isn't the principal ideal. But yeah. So just say the zero ideal. That's a good question. Okay. So all right. So then we're gonna let T. So we're gonna take a chain, right? So let T here be a collection is in A. This is some index set. So let this be a chain. Okay. So then what are we going to do? Then then what we're going to do is form the ideal here. So this is a chain, so they're all comparable. And so what we're just going to do is we're just going to take the union of everything. This is like a theme here. Okay. This is actually an ideal. So you can check that this is an ideal. It just is because, so normally unions of ideals are not ideals. Okay, if I just took two random ideals and I took their union, that's not an ideal, right? It turns out that these are all nested, right? And since they're all nested, then if you take two elements and you want to subtract them, right, then they're both going to be in some high enough index, right? And then so once you have them in the high enough index, right, then you can subtract them, and then they're in that element for that ideal of a fixed index. Okay. All right. Okay. So I tilde up is an upper bound for the chain T. So every element in here is less than this element. And so, of course, like this partially ordered set, this is under inclusion. Okay. All right. So what do we got? Okay. So now by Zorn's lemma, S has a maximal element. So that's a maximal ideal. Okay. All right. So that proves the first thing. Okay. So we proved that that all rings have maximal ideals. Okay. Now, for the second part, is there any questions?
Just kind of clarifying the fact that none of those I sub alphas equal R means that there's no way the union could either, right?
No. Nope. No. That's a pretty good question, actually. Let's see. Why can they not be equal to R? So, I mean, I guess you have to show that 1 is an element of the ring, right? And so, right, and so if 1 was an element of this, right, then 1 would have to be an element of I alpha for some alpha, right? Which would contradict that these are proper.
Makes sense. Easy. Okay.
That's a great question. Okay. So, any other questions? Feel free to interrupt at any time about any of the material, and yeah, I'd like to keep everybody talking. All right.
It's pretty straightforward to say that this is a partial ordering. We kind of just said that at the start.
Yeah. So why is it a part? If you believe that, yeah. So this is pretty straightforward to show that it's a partial ordering. So what do you need to show? So you need to show that it's reflexive and transitive, right?
Right.
So okay. So if you have I is an ideal in J and J is an ideal in K, right? Then I is an ideal in K. Right. That's transitivity, and that just follows from transitivity of subset inclusion.
Right.
Okay. And then reflexivity is easy. So I is contained in I.
Right. Okay. That's what I did in my head. I just wanted to make sure that that's like
it's all induced from the power set of R, right? Okay. So this is like a sub poset of the power set subset, the power set poset of R.
Okay. Cool. Yeah.
Yeah. Okay. Great. So we have the existence of maximal ideals, right? Now we need to show the existence of maximal ideals above a fixed ideal, right? So what you do is you just apply the exact same trick. To the set S, which is the set of ideals in R that contain I. And J is not equal to R. Right? So now you just do the exact same thing, but you just impose this extra condition here that J needs to contain our fixed ideal I. Right? So what are we showing again? We're showing that for every ideal, right, that is not maximal, right, there's some maximal containing it. Or that's not the whole thing, right? It could be itself, right? It could be a maximal ideal itself. Yeah, you just do the exact same thing. All right. So now we have that maximal ideals exist. Okay. So I want to do some PID stuff. Okay. So now I'm just gonna switch some topics and okay. So we're gonna do PIDs, UFDs, Euclidean domains. All right, so this is kind of a new topic here. Okay, so the main theorem, I'll just state what the main theorem is. Okay, so the main theorem says that if R is Euclidean, this implies R is a PID, and this implies that R is a UFD. Okay, so there's kind of this hierarchy of inclusions, and so this is where you have unique factorization. Into prime elements. Okay, and this is like things that have the division algorithm. And in the middle one are principal ideal domains, which we've talked about. So all of the ideals are principal. The ideals are essentially small. Okay, so okay, so let's kind of do a little warm up here. Okay, so if A, so the warm up is that if A is contained in the ideal B in some ring, right? This is if and only if B divides A. So there's this relationship between divisibility and containment of ideals, right? Why is that? Well, so this means that A is contained in B. In particular, the element A is contained in here, in B. And so that means that A looks like B times something else, right? And when so when A looks like B times something else, that means B divides A. That's exactly the definition. Okay. So all right. So let me say, so maybe we can do the Euclidean domain thing first, because I know that we're going to finish this off. Okay, so let's prove that, let's do some Euclidean domains first. Oh, what happened? Let's see. There we go. Okay. So let's do Euclidean domains. All right. So let's give the definition. So like I said, it's something with the division algorithm. So a Euclidean domain so it's called Euclidean because of Euclid's algorithm, and Euclid's algorithm is just the division algorithm, right? So it's a ring with a map N. There's a ring R, or let's say I should say it's a domain R. Actually, let's do a fun game, right? I don't know if we need the domain hypothesis. Is a domain R, right? Such that there exists a map, and this is maybe called the Euclidean norm. Not maybe it is greater than or equal to 0, with the following properties. 1, n of 0 is 0. 2 is that for all A and B in the ring, if the Euclidean norm of B is bigger than the Euclidean norm of A, there exists some two elements, Q and R, in R, with the norm of R strictly less than the norm of A, such that we can apply division. We can do the division with remainder. B is equal to QA plus R. Okay, so this is what a Euclidean domain is. It's such that one of these things exists. Okay, it's not necessarily fixed. You can develop the theory with a fixed thing. It doesn't really matter, right? I could have defined this to be a Euclidean domain is a pair R with an N, but I'm just going to say that there exists one. You know, the part of the definition doesn't really matter, right? Okay, so two examples. Let's do three. The integers, right? And then this is using the normal, I guess, then the norm of x is the absolute value of x. Two, the Gaussian integers. Showing this one's a Euclidean domain is a little bit more complicated, and I'm going to leave this as an exercise. So the norm of a plus ib is going to be a squared plus b squared. So this is actually this is also equal to the complex norm, right? So the complex norm squared. Okay. So this norm is not a norm in the sense of like you know, Mike Wilson's class. Okay, it's an algebra thing. Okay, so if F is a field, then F adjoin T is a Euclidean domain. Okay, what's the norm here, do you think? It's the degree. Okay, and so the division algorithm here is just polynomial long division. Okay, so usual polynomial long division. Okay, so I would encourage you to go read the section on, there's like a little example of the Gaussian integers in Dummett and Foote, and you should definitely go read that. About how that works. Like the Gaussian integers are something that just like always pop up on quals. Okay, so let's prove a theorem. Let's prove that the first part of that theorem, right? So that every Euclidean domain is a PID. So all right, let's do the proof. All right, so so let R be a Euclidean domain. I use R a lot, huh? With norm n. Maybe I should not use R so much. Okay. So let R be a Euclidean domain with norm n. So we need to show that every ideal is principal, right? So we need to show every ideal is principal. Okay, so what are we going to do? We'll let I be an ideal. Okay. Okay, so now I'm going to do the first thing. So here's the trick. Okay, so the generator is the element is any element of smallest norm. Okay, so the generator of an ideal in a Euclidean domain is an element of smallest norm. Okay, so let A be an element of R. So be an element of the ring. So let A and I be a non-zero element of minimal norm. Okay. Okay, so let's show. Okay, let me just make a little comment here because I think someone might say something. Okay, we can suppose that I is not equal to 0 since you know, since let's do it like this. Since the 0 ideal is generated by 0. Okay, so let's suppose it's not 0, so then we can take a non-zero element. All right. Does anyone want to talk about why the non-zero elements of a minimal norm exist? Right. Okay, let me just say why this exists. So in an ideal, right, you can just take all the elements in the ideal, right, and then I can take all their norms, right? That'll give me a collection of non-negative integers, right? Right. So that's just a bunch of integers. Any set of integers, any subset of integers has a minimal element by the well-ordering principle. Okay. And because that's an element of the set, there exists an element A of that norm. Okay, so such a thing exists. All right. Okay, so now what we're going to show is we're going to show that so we will show that I is equal to A. Okay, so what we'll do is we'll let B be an element of I, just be any other element. Okay, and then there's two cases. Case 1, right, is if NA is the same, if they're of the same norm, right? Then, oh, actually, I think I can do it without cases. Let me try this. So I don't have to do this. Okay. Then, so we know that the norm of B is greater than or equal to the norm of A. And so here's something that you need to be careful about in the definition. Okay, it's a technical point, is that in this definition, you need a greater than or equal to, not greater than. Okay, so this thing is just to point this out here. If you forget, if you use greater than, you're going to have a not a good time. Okay. All right. Okay. So we know that this is bigger than this. So by the axioms of Euclidean domains, so B is equal to QA plus R for some QR in the ring with the norm of R strictly less than the norm of A. Okay, but this allows us to write, allows us. Okay, so let me just say, let me just do something here. So if we take this, so this tells us that B minus QA is equal to R. So this implies that R is an element of the ideal, right? Because this is an element of the ideal and this is an element of the ideal. And if I subtract two elements of the ideal, right, you get something in the ideal, right? Okay, so this little remainder is in I. But so if n of R was not equal to 0, then this would contradict the minimality of A. So hence this implies that the norm of R is 0, and R is equal to 0. So that was one of the axioms. Okay, so this tells us that B is equal to QA. So B is an element of the ideal generated by A. Okay, so this proves that I is contained in A, and then clearly A is contained in I, since A is in there, right? And so this means I is equal to A, right? So we showed that every ideal was principal. Okay. And the trick is that you just do division with remainder. The trick is take the smallest element. Okay, that's the trick. Any questions on that? Okay. So here's a good exercise. Well, this is what I was going to do in the thing. So if NA is equal to NB, then A and B are associates. Well, actually, let's say actually, I don't know if that's quite true. Let's see. Oh, what's going on here? Where am I? What the heck? What I was gonna, yeah.
I was just gonna ask a quick question actually about the last thing, if that'd be all right, real quick.
Yeah.
Why does why can't the norm of R be non-zero? I get that it would contradict minimality of A, but why can't the norm of R be non-zero?
Yeah, so we suppose that A was an element of minimal norm, right?
Right.
And R, so R is in the ideal, right? And if NR was strictly less than the norm of A, then A wouldn't be minimal.
Why can the norm of R not be greater than? Oh, it says that for some Q and R with N of R less than.
It's the axiom. Yeah.
Yeah. Thank you.
All right. I don't know what's going on with my computer here.
I think you just like super zoomed into the board, that's why you can't see anything.
Yeah, but it's not even responding. Let me refresh. All right. Let me go back to here and see if I can get.
And maybe I'll just. Keith, I was just going to say that this is modeled after just the usual division or remainder. So like 10 divided by 3. Yeah.
Yeah, no, I think when I wrote it down right away, just I saw an A and I thought it was a Q, so I wrote down Q instead of A in the axiom.
You have to right click.
Yeah, thank you. And thanks, Rick.
Yeah, for sure.
Okay. Okay, so if A and B, so in the okay, so what I was going to say is, let me just get rid of this here. So what I was going to say is in the above proof, if I was going to break it into cases where the norm of A and B were equal, and in that case, you would have shown that they were associates, right? That those two things were just multiples of each other, unit multiples of each other.
If A divides B and B divides A, is that kind of a slam dunk that they're associates?
Yeah, in a domain that they'll be associates. Oh, we were going to play that trick, right? Oh, here's the game that we were going to play. Did I use that this was a domain? I don't think I did. Did I? Yeah, I don't think I used the fact. So I don't think you need this to be a domain for this to work. So I think that this proof just follows. Maybe it'll imply it's a domain for some reason. I'm not sure. So you don't get that associates thing if A divides B and B divides A. For that to work, you definitely need a domain, right? But anyway, yeah, it's kind of a fun question, I guess, to see if you need it. All right. All right. So now we were going to do UFD stuff. Okay. So, all right. Okay. So let's do some PID stuff. So, okay. So let me prove a theorem. Okay. So theorem. Okay. So now I'm moving away from Euclidean domains, and let's do. Did this have a subsection title or no? Okay, yeah. All right, PIDs. Okay, so let's do a lemma. So every prime ideal in a PID is maximal. So let R be a PID. Every prime ideal is maximal. Okay, so they're kind of very small, right? In the sense that like they don't have very many ideals. Okay, so what we're going to do is we're going to let P be a prime ideal. A prime ideal. And suppose that M, suppose that M, and we can write it as M, is an ideal containing P. This ideal generated by P. Okay, so what we're going to show is that, to show M is equal to P, or M is equal to the whole ring R. Okay. So all right. So first we're going to use that. So we're going to use that little warm up thing. So by the warm up, we know that M divides P. Okay. Also, by the exercise, so P is a prime element, right? So P is irreducible. So that was one of the things that I was going to have you guys do, is show that every prime is irreducible. Okay. All right. So okay, so this shows that M divides P. So by definition of irreducibility, what does this mean? So by definition of irreducibility, by definition of irreducibility, M is either a unit or an associate of P, right? Okay, and so if M is a unit, right, then M is this ideal here, M is equal to R. If M is an associate of P, then M is equal to P. Right, and that proves maximality, right? Because we showed that it is either, it was either the whole ring or a proper subring. Oh, sorry, it's either the whole ring or the ideal, the same ideal, right? And that's what it means to be maximal. Okay, so I think I'm going to stop here. The thing that we have to show next is that if R is a PID, irreducibility is the exact same thing as prime. So I'm going to show the other way that irreducible implies prime, and then we're going to have a discussion of why PIDs are UFDs, right? And yeah, and then I guess I'm going to do one example of like showing you an example of a ring, how to show. So like there's a common qual question where they'll give you a ring, they'll be like, show it's not a UFD, and so we'll show that certain elements are irreducible and that their factorization is not unique. All right, so I'm going to stop the video and then we can ask more questions after if you guys would like.